So this video is for Math 112, and this is for a handout on using vectors and trigonometry on problems that have to do with traveling or motion in the face of wind, okay, or a counter force of some kind. Let's take a look at some of these problems. So the general idea here is that we'll be given an object, a plane or a boat of some kind, that'll be traveling in a particular direction. Okay, we'll talk more about that as we go through the problems. And then you'll have a countervailing force, which is either a current in the water or wind in the air that is also blowing from a particular direction in a given direction. And again, I'll talk more about that as we look at the problems. The general idea, so if this vector represents the airplane's path and speed, so it has a magnitude and direction, which makes it a vector, then this vector here would represent the magnitude and direction of the wind. And so to determine how the wind affects the travel of the airplane, here actually let me make this wind vector red. What we want to do then is attach the wind vector onto the end of the vector for the airplane. And the resulting vector will indicate the resulting path of the airplane and speed of the airplane. Sometimes if an object has a headwind, it'll slow it down. If it has a tailwind, it'll speed it up. And if it's coming in from the side, it'll push it off course by a certain amount, depending on how strong the wind is. So let's look at some problems. Before we get into this, a lot of these initial problems just use the directions north, south, east, and west, and sometimes northwest, and we can get angles from that information. But some of them use this method of describing a direction with a bearing, which is a clockwise deviation from north. So a bearing of, let's say, 50 degrees would look something like this. Okay. Bearing of 100 degrees, and I'll put in the other directions here. Bearing of 100 degrees would look something like this. Right? 150 degrees would be down here. Let's say 300 degrees is over here. Okay? If you rotate all the way around like that, then that would be 300 degrees. Okay? So we'll see a few examples of that on this handout. On the other handout, there are many examples of that, and I'll talk about those problems in a separate video. Okay, so let's just start working through the even problems on this handout here. Problem 2, a plane is headed due west with a speed of 300 miles per hour. Okay, so let's draw this, and we'll put the plane in here. Well, I'll use the purple for the plane. And so it's headed in that direction. And the length of that vector there is supposed to represent the speed of the plane, which in this case is 300 miles per hour. The wind is from the north. Okay, so that means it's blowing north to south. If we were to draw a vector from the center of our diagram, then it would look like that. But to find out how it's going to affect the airplane, and let's see, what's the speed on the wind? 80 miles an hour. Okay? To find out how it's going to affect the airplane, right, we put it onto the tip of the vector that represents the airplane. Okay. Then we connect the center of our diagram with the tip of the wind vector, and the length of this will represent the what's called the ground speed of the airplane. It has an airspeed of 300 miles per hour, but that doesn't take into account how the wind is affecting it. The ground speed will take that wind into account. And also, we're going to find out what is this deviation from the planned flight path of the airplane. Now, in this problem, and the first couple problems are like that. In this problem, you've got a 90-degree angle right here, right? This is going due west. The wind is blowing from due north to due south. That makes that 90 degrees, okay? So we don't need the law of sines or the law of cosines to solve this problem. You can use it if you want to. But what we really need to do here is we can find the ground speed of the plane. We can find the length of this vector just by using the Pythagorean theorem. 80 squared plus 300 squared. I'll call this x, and that'll be equal to x squared. So let's see what we get here. 80 squared and 300 squared, 96,400. And then we'll square root that. And that tells us that the speed of the plane is going to be about 310.5 miles per hour, the ground speed. It's being pushed along by the wind a little bit faster than its engines are running. Okay, or it's adding to the speed that it's getting from the engines. And then the deviation from the flight path, if we call this theta, then we can say, tangent theta is going to be 80 over 300. And so if we take the inverse tangent, let's make sure I'm in degrees here. Yes, okay, good. So inverse tangent of 80 over 300 tells me that theta is going to be about 14.9 degrees. And so although it's flying due west, which is a bearing of 270, right? Due west is a bearing of 270 degrees. If you start from the north, rotate clockwise this way, there's that 270 degrees. The actual flight path for the plane will be 14.9 degrees less than that. And so the actual bearing for the plane is going to be, what is that, 255.1? Let's see. So that looks right. Okay. And we can round this to the nearest whole degree if we want to. It's close enough to do that, but I rounded it to the nearest tenth. All right. So there's the information we're looking for, the ground speed and the actual path of the airplane. Okay, and that one is problem 2. Now these will get more difficult when this is not a 90-degree angle. It'll get a little bit trickier. We'll work with those problems in a few minutes. Okay, let's take a look at problem 4. All right. Problem 4, a superlight aircraft is flying northwest at 75 miles per hour. So there's our northwest path. We've got 75 miles per hour there. And so the bearing that the airplane is trying to fly on is, let's see, that's going to be 270 plus another 45. So that's going to be 315 degrees on that bearing, right? If we go clockwise around from the north, that's 315 degrees. Okay, now what's the wind doing in this situation? The wind is from the south, so it's blowing south to north. So that means if we want to put it onto the end of the airplane's vector, it'll look something like that. And that one is blowing 40 miles per hour. Okay. Now, to get the actual path of the ultralight plane and the ground speed, here, let me put that 75 MPH down there. Get that out of the way. So here's the actual path and the length will represent the ground speed of the airplane in this situation. Okay, so now this one, it's a little bit trickier to find the angle. I mean, mainly what we're looking for is we need to find this angle in here. Okay, so let's see kind of what that looks like. So this blowing south to north is parallel to this line right here. So if we take those two, okay, so here's the airplane's vector that represents 75 miles per hour, and here's the wind vector that represents 40 miles per hour. Okay, there's the north-south situation. Okay, so we know that this in here is 45 degrees plus this 90 right here tells us that this angle right here is going to be 135 degrees. Okay, and then if we use alternate interior angles, that says this angle over here is also 135 degrees. There are a variety of other ways to come out with those values, but that's what we're saying is that this angle right here is this angle inside that triangle, and that is 135 degrees. Okay, now for this triangle, we will need the law of cosines. So, if we want to find the value, magnitude of that vector that represents the actual ground speed for that ultralight plane, we're going to be finding x, and we'll say x squared is going to be 40 squared plus 75 squared minus 2 times 40 times 75 cosine 135 degrees. Okay, so let's see here. 40 squared plus 75 squared is 7225. Now this, because that cosine 135 is going to be negative, this is going to end up as a positive. You'll have the negative there and the negative from the cosine. And let's see what we get out of this cosine 135. 42.64. And we add that on to the 7225. And so our x squared will be about 11,467.64. And if we square root that, then we get an actual ground speed of the airplane of 107.1 miles per hour. So notice, if the wind were blowing in exactly the same direction, it would push it along and make it 115 miles per hour, okay? If it were blowing a headwind, you would subtract just 75 minus 40, and your actual forward motion would be 35 miles per hour. Because it's blowing on an angle, it is adding some speed to the plane, but not quite as much as the speed of the wind itself. Okay, so there's the magnitude of the ground speed for the airplane. And then let's see, we need to find that deviation in the flight path there. And so to do that, we can use the law of sines. Let's see here, I'll call this theta in there. And we'll say sine theta over 40 equals sine 135 over 107.1. So let's see what we get here. Sine 135 divided by 107.1 times 40. And then take the inverse sine there. And we find out that theta is about 15.3 degrees. In addition to the 315 that was the original bearing, or the desired flight path. And so that's going to make the actual bearing for this ultralight aircraft of 330.3 degrees. Okay, so this process of pulling out the vectors and looking at them on the north, south, east, west grid can be very helpful in determining what these angles are going to be. Okay. All right, let's look at problem 6. Okay, let's see here. So the helicopter is headed on a bearing of 240 degrees. So this is 270, this is 180, 240 is going to be about right there. Okay? And that tells us that this angle in here is 30 degrees. And let's see, if that's 240, then this one is going to be 60 degrees. And the magnitude of our vector there is the helicopter, 195 miles per hour. Okay. The 70-mile-an-hour wind is coming from a bearing of 5 degrees. Okay, so here's the bearing of 5 degrees. That's the direction it's coming from. So it's blowing in this direction. So we want to take that vector and we want to put it onto the tip of the vector that represents the path of the helicopter. And so it'll be kind of something like that. Okay, and then this will be 70, actually, yeah, I'll keep that, 70 miles per hour. So that's a very strong wind. It's going to have a significant effect on the helicopter. Let's see, let's make some space in here because we want the resulting vector to represent the actual ground speed for the for the helicopter, and then also we're going to find this deviation from the desired flight path in there. So here's our parallel vectors. Okay, so let's see here. We've got our north, south, east, and west, and then we've got, there's one of the wind vectors. Here's the helicopter vector, and then here's the other wind vector over here. And what we want to know is what's this angle in here. Okay? Let's see here. So let's cross these like this. So that's going to match this angle right here, right? Those are corresponding angles. And a lot of this comes from this, you know, two parallels cut by a transversal, where all these angles are the same measure. These angles are all supplementary to the other ones, and they're all equal to each other as well. So these two match up with each other. Let's see if we can find out what that angle is right there. Let's see here. So that purple vector right here represents the path of the helicopter that had a bearing of 240 degrees, right? And so we said this was 30, this was 60. So what I'm interested in is this piece right here, okay? Because that's going to be, let me label these. We've got like 1, 2, 3 little pieces in there. There may be another way to dig out the value of that angle, but this is how I'm going to approach it. This angle in here is 30 degrees, right? It is a vertical angle to this angle in here, which is 30 degrees. Okay, so that's good to know. And this second part in here, this is a right angle. It's the whole quadrant down here, that's 90 degrees. This piece right here is a vertical angle with that section up here, that's 5 degrees, so that's 5 degrees right there. So this looks like this whole angle right here is going to be 125 degrees, and there it is right there, 125 degrees. Okay. There are other ways, like I said, there are other ways to figure out the values of these angles. Whatever works for you is wonderful, okay? So long as it's correct. All right, so now that we know that, let's see. And this right here is 195 miles per hour. So if we want to find x using the law of cosines, we're going to say x squared is 70 squared plus 195 squared, 2 times 70 times 195, times the cosine of 125 degrees. And again, because this is an obtuse angle, we're going to end up with a positive right there. So 70 squared and 195 squared make 42,925. And then the second piece, -2 times 70 times 195 times the cosine of 125 degrees, 15,658. 0.6, let's say. And add that on to the 42,925, 58, 583, 0.6 for x squared, and let's square root it. Says that the ground speed for the helicopter is going to be 242 miles per hour. Let's see. Is that possible? Well, if the wind was blowing directly behind it, it would be adding 70, which would make it 265. It's not quite blowing directly behind it, but it is adding considerably to its speed, 242 miles per hour. Okay, now let's find the value of that angle theta so we can know what is the actual flight path for the helicopter. So we'll say sine of theta over 70 is going to be equivalent to the sine of 125 degrees over 242. So sine of 125 divided by 242 times 70. And then we take the inverse sine, about 13.7 degrees. Okay, so the original bearing was 240, and we want to subtract 13.7 from that. So the actual flight path for the helicopter will be along a bearing of 226.3 degrees. Okay. All right, we got one more to look at, problem 8. Let's see what that one looks like. All right, a cruise ship traveling 16 knots on a heading of 330 degrees. Okay, so 330 degrees is going to look something like this. Let's see here. So the speed, the magnitude of that vector, 16 knots. And because this is 330 degree bearing, then we know that this angle in here is 30 degrees. And we'll worry about that when it comes time to look at the triangle and see what the angle we need, where the angle we need is going to be positioned. All right, there's a strong current flowing at 6 knots from the south to the north, okay? So it's flowing, this current, from the south to the north at 6 knots. And so we're going to take that vector and attach it onto the tip of the travel vector for the ship, and that will represent 6 knots. Okay? And then the actual speed and direction for the ship will be given by that resultant vector right there. Let's take that 30 degrees out of there because it's kind of in the way. So we need to find the length, the magnitude of that vector. I'll call it x. And then we want to find that angle in there, theta, and what's the deviation from the original bearing for the ship. Okay, so we need to know what's this angle in here. So how can we do that? Let's see here. What we've got is a situation like this. So there's the wind vector, and there's that. Let's see here. So without this purple resultant vector in the way, remember that whole piece right there was 30 degrees, right? Because the original bearing for the ship was 330 degrees. So that means that that piece inside there is 30. And this is the north-south line right here. And this is the vector for the wind added onto the tip of the vector for the ship. Okay, so if this is 130, this is 150, that means, I'm sorry, this is 30, this is 150, that means this is 30, and the angle that we're interested in is also 150 degrees. Okay, and notice that it's easier to do this with the angles when you don't have that resulting vector, okay, in the picture. It's a lot easier with just the original bearing of the ship and then the wind or current tacked onto the tip of it. It's a lot easier to look at this diagram and pick out what's the value of the angle that we're going to need here. Okay, now that we've got that, now we can set up the law of cosines to find the magnitude of x. So that's going to be 6 squared plus 16 squared, 2 times 6 times 16 times the cosine of 150 degrees. And again, we've got a obtuse angle in there, so this is going to end up a positive value. So let's see what we get here. 6 squared, oops, okay. It looks like we've lost power here. Not sure why that is. And that is very inconvenient as we were just completing the last problem. Let's see if we can get a little bit more light in here, and then I will wrap this video up. Okay, so we were just about to finish problem 8 here. Let's see if we can do this. 6 squared and 16 squared make 292. And then over here, negative 2 times 6 times 16 times the cosine of 150 degrees gives us positive 166.3, we'll say. And then if we add those together, what do we get? 458.3. And square root it so that our resulting speed is 21.4 knots. 21.4 knots. Okay, now we've got to find this angle theta in here, and so again we need the law of sines. So we'll say sine theta over 6 should be equivalent to the sine of 150 over 21.4. Okay, so let's see here. Sine of 150 divided by 21.4 times 6, and then we take the inverse sine. About 8 degrees is what we're seeing here. Theta is about 8 degrees. And so the original bearing was 330 degrees, and so the resultant bearing coming from the current is going to be 338 degrees. Okay, well, that's it for this video. I'll take a look at it after I wrap things up here, make sure that you can see this last part of it. As always, if you have any questions, please let me know. Thanks.